Hello, and welcome everyone to the Juno press briefing at the joint meeting of the Division for Planetary Sciences and the European Planetary Science Congress at Pasadena in California. My name is Shantanu Naidu. I am the press officer of the Division for Planetary Sciences. Today we have three speakers who will give us Juno's mission status update and science updates. On my left is David Schurr, Deputy Director for Planetary Science at NASA. To his left is Scott Bolton, Juno Principal Investigator at the Southwest Research Institute. To his left is Candice Hansen, Juno Co-Investigator at Planetary Science Institute. Before we begin the presentations, I would request everyone to silence their cell phones. After all the presentations are done, we'll take questions from those present here and members of the media watching online. And with that, I'll pass it off to David Schurr.
Good afternoon. Today we'll be updating the science and mission status from Juno. Juno successfully arrived at Jupiter July 4th of this year. It's the second of our New Frontiers missions. New Frontiers is our program that solicits PI-led, competitively awarded, what we call medium-class missions for planetary science. The last 18 months have been very busy for the New Frontiers program. We have the first in our series, New Horizons, flew by Pluto July of last year and is on its way to a Kuiper Belt object for January 2019. The third mission that had been selected in this series was OSIRIS-REx, which launched successfully last month, and it's on its way to Bennu, a near-Earth asteroid. It'll arrive in 2018 and ultimately bring back a sample. And we've been talking about New Frontiers 4. It's the next announcement of opportunity for this program. Will come out by the January timeframe. So in the last 18 months for a program that's been around for quite a while, we're starting to get some science, and you'll hear today about what Juno has discovered. We did notify late last week that we had postponed the period reduction maneuver that was planned for today, and instead had replaced it with a science pass. As of last evening, 10:47 local time, the spacecraft did go into safe mode, so the science pass was not performed today. All the instruments were turned off as part of the safe mode. And Scott will talk to you about the current status of the spacecraft as well as the science that we've seen so far. With that, turn over to Scott.
Okay, thanks. I'm Scott Bolton, the Principal Investigator for Juno. I'm going to talk to you about a couple of different topics. As you heard from David, the spacecraft went into safe mode last night. So I'm going to address that. And of course, the delay that we had for our rocket firing, which was originally planned. And then I'll go into the fun stuff, the science. And so as we speak right now, the spacecraft has just passed Jupiter. So we had a perijove, which is when you get really close to Jupiter. We get about 5,000 kilometers or about 3,000 miles away from its cloud tops. And so within the last hour, we've actually gone that close and are starting to move away from the planet. The spacecraft's in totally safe condition. Everything's working and functioning as normal right now as we pass that. Now, what happened was on the way in last night, when we were still pretty far away from Jupiter because we're moving really fast, the spacecraft went into a safe mode. What that means is that the spacecraft, it's like a smart robot, has a very smart computer on it, detected a condition that was not expected. It did exactly what it was supposed to do when it detects a condition that's not expected, is it evaluates the situation and then takes an action. In this case, it turns off unnecessary subsystems. It points itself, and if not already pointed, to point at the sun, go power positive, link up the communications to the Earth, and then wait for direction and for the humans back home to evaluate the situation and decide what the next forward step would be. So it did exactly what it was supposed to do. That software is called fault protection. It's worked perfectly. the situation at this point is where we just passed through Jupiter, and the impact was that we shut down our science instruments in order to make sure that nothing unnecessary was being done on the spacecraft as we went by Jupiter. So we went through another set of radiation belts, and nothing else happened that we are aware of at this point. Now, that was part of a plan prior that we were on this particular orbit. We were going to fire our rocket motor. We call it period reduction maneuver, PRM. And what that was going to do, it was the same rocket that we used at Jupiter orbit insertion. It was going to slow the orbit down even more as we passed by Jupiter and change the orbit from being 53 and a half days long to 14 days. And then we would be going around Jupiter every 2 weeks. And after, when we were preparing for that, we detected as we were pressurizing the propulsion system, basically, we were turning on getting ready to fire the rocket. We noticed a different condition in the valves that actually open up and pressurize the system. They behaved with a little bit of delay, which meant maybe the valves were a little sticky. We didn't want to take any chances that some adverse type of condition would cause the burn to go in a way that we didn't expect. And so we decided to postpone and delay that burn. And at that time, we did it early enough that we were thinking that we could turn this flyby into a science pass and get some science. Of course, the spacecraft safe mode condition eliminated the science, but everything's okay, and we retain the ability to do that rocket firing sometime in the future. So we have a couple of tasks that we have to do. One, we have to go analyze and understand what just happened with the spacecraft safe mode entry and make sure that that's all working and understood. And we also are going to go in and look at the valves and what was going on with the propulsion system. Basically, every propulsion system on all spacecraft have a fairly complex plumbing system. You can think of it as just a plumbing system that's had a little bit of unexpected behavior to it. So we will go in and analyze that, and then once we figure that out, we'll decide where to go next. We're in no rush to make any of these changes. Fortunately, the way we designed Juno in the orbit that we went into was very flexible. It allows very flexible science. So the science that we get on Juno, all of the goals and objectives is tied to the scientific investigation of Juno, are really related to the details right around perijove. So let me show you what that looks like. So here's a figure of a perijove trajectory, and you can see here's Jupiter and the trajectory going by. So these time ticks are about 1 hour. So you can see it takes about 2 hours to go from the North Pole to the South Pole. We're moving very, very fast. It's in that time frame where the critical science that Juno obtains in order to accomplish its objectives. That's where it's obtained. And so the difference between the trajectory I'm showing you here, which is a 53-day orbit, and if I were to show you the 14-day orbit, it basically looks the same. The difference is how far away you get from Jupiter, but the close-in geometry right around Jupiter is almost identical. So we can obtain all of the science goals of Juno even if we stay in a 53-day orbit. Each pass has the same value that a 14-day orbit would have passed. We were changing to 14 days primarily because we wanted the science faster, but there was no requirement to do that. So with that, I'm going to go on to the science. So keep this picture in mind because this is actually a picture from PJ1. So this is the trajectory that we used back on August 27th. And the science data that I'm going to describe to you today, it comes from that day primarily, or that approach and after. And so this is what the trajectory looks like. And you can see the orbits of two of Jupiter's Galilean moons here to guide you in how close we are to the planet. So there's Io and Europa, the two red circles, and the inner gray one is Amalthea, which is a moon that's embedded in Jupiter's radiation belts. And so you can see that what we do is we come in from the north and we slide between the radiation belts on Jupiter and out, and that's basically the design. And so where we are today is not much past where the spacecraft is shown on this trajectory. Right now, we're basically in an orbit that's just where the blue spacecraft is just a little bit below what you see right now. That's where we are right this second. Okay, so one of the investigations on Jupiter is called the microwave radiometer. We call it MWR for short. It's actually 6 different instruments. They're all microwave radiometers. They're basically antennas that measure radio, and the radio frequencies are in the microwave regime. And here you see on this particular graphic 5 of those antennas. I show this to you so that you can understand that this instrument is not like what you might think of as a radio antenna. They don't look like your DirecTV dish antennas or even the Deep Space Network's dish type antennas. These are flat panels, and each one is customized specifically to be used at Jupiter as part of this Juno investigation. Here you see 5 of them. Each one is a different frequency or wavelength, and the larger ones are the lower frequencies or longer wavelengths, and then it gets progressively smaller. And at the very top, I'll show you here, this is the horn. So when I get to a high enough frequency, it almost looks like a horn, like a musical instrument. And then here's the next one, and the next one bigger, and they keep getting bigger. And that's this instrument was basically invented for Juno. This is the first time this instrument has ever been used. Nobody's ever created an instrument like this, and its primary objective is to look at Jupiter's atmosphere and see beneath the clouds. And that's what it's helping us see the invisible. So on the other side of the spacecraft is the largest antenna, the lowest frequency, the thing that sees the deepest into Jupiter. And in fact, this particular antenna is what drove the design of Juno. We wanted the largest antenna we could, and so we designed this antenna, and basically the spacecraft was built and designed around this antenna shape and size. And again, even though it doesn't look like a radio antenna, it is a very advanced one. Okay, so this particular instrument gets to see beneath the clouds. So if we were flying by Jupiter and you had X-ray vision, you might be able to see beneath the zones and belts and the beautiful stripes that Jupiter has, and even see how deep are the roots to the great red spot and things like that. And so you can imagine if Jupiter has different layers of its atmosphere as we go down. It's a giant ball of gas, and they have different layers as we go down into the atmosphere. This instrument's capable of basically peeling those layers back as if Jupiter was an onion, right? And I can peel off the layer of that one by one of the onion and see what it's like inside. And so I'm going to show you for the first time an artist's conception based on our data to see what Jupiter looks like underneath. This came from the first and only pass right now on August 27th, where we had this instrument on. We will get many of these passes in the future. But in the very first one, you see, okay, so here's Jupiter from a visible cloud, the visible clouds that you would see from a normal color camera. Okay, so this is what Jupiter looks like to most of us. It's all recognizable. Here's the great red spot. Okay, so you see these zones and belts, the orange and white and gray stripes. And as you look down to the next level, that's our first high-frequency receiver, and then each level goes to the longer and longer wavelengths until I see all the way down. When I get down to the bottom here, the lowest layer, I'm looking about 350 to 400 kilometers into Jupiter. Okay, and the first thing you can see from this is that the structure of the zones and belts still exists deep down in Jupiter. So whatever's making those colors, whatever's making those stripes is still existing pretty far down into Jupiter. So that came as a surprise to many of the scientists. We didn't know if this was very skin deep, just a really thin layer, or whether it goes down. The other thing that is surprising and very interesting about this is that while the zones and belts appear to exist deep down, they're evolving. They're not staying the same. They're changing as we go down, and you can see that by the fact that this one changes as we go down, and actually it becomes less apparent way down, but it still starts moving around. Some of this white is orangey down here, and then this one seems to disappear, and another belt goes down here. So deep down, Jupiter is similar, but also very different than what we see on the surface. And this tells scientists, and we're still evaluating this, I can't tell you all of what this means yet because we're still interpreting it, but what it's telling us is hints about the deep dynamics and the chemistry of Jupiter's atmosphere. And this is the first time we've seen any giant planet atmosphere underneath its layers. So we're learning about atmospheric dynamics at a very basic rate and level. Okay, I'd like to jump to another instrument, which is the JunoCam, which is our visible camera. And if it was used, it would take a picture of Jupiter that looks just like this. Except we used it when we went over the pole. We got some pictures like the other one as well, but here's the first picture of Jupiter's poles that we took on August 27th. And this was pretty remarkable because it told us right away some things new about Jupiter's atmosphere, and in particular the polar. The first thing is there was no hexagon shape like you see on Saturn with Cassini. So we weren't really sure what the poles look like, but you can see clearly there's no hexagonal shape of the storms. The second is you see many of these cyclones around, some of them small, moving very quickly. These are things that are seen a little bit at the lower latitudes, but not as many, and the poles are filled with these things. And that was kind of a surprise. And then lastly, what I'm going to focus on right now is as we came across, we're always flying over the terminator. That's our orbit. It's called dusk dawn. So we fly around the terminator, which is where the sunlight stops, right? That's what this shadow is. Jupiter's always half lit here to us. So we're flying right across this. And when we look down, of course, when you see something on the terminator, you can see topology, or you can see the 3D effects a little bit. So when I give talks at schools, if kids are saying, I got a pair of binoculars or I have a telescope, what should I look at? I always say the first thing you should look at is look at the moon and look right at the line, the terminator, where the light and shade are, because that's when you can see the craters and the moons. You're seeing topology, right? You can see the 3D effects. We're seeing for the first time the 3D effects of Jupiter's atmosphere. And I can show that to you. And this came as a surprise to us as well. Right here, this one cyclone shows shadows, which right away told us this part of that storm system is elevated above Jupiter's base atmosphere. Now, if you were to ask me why didn't I think of that before, I would say I should have. That the reality was, is if you think about it, the Earth's atmosphere is a little bit like that. You go on an airplane, you see different layers of clouds. So Jupiter must have had that, but nobody had ever been able to see it before. You just had to get lucky and go. Of course, we're going to go over the terminator many times, and so we may see many examples of this in the future. But on the very first pass, we got lucky and we saw one. One of these cyclones has to be just in the right spot in order to see that shadow. Now, here's a close-up of that shadow, and you can start to see the shape. And so what's amazing about this shadow is so we've done some calculations based on this first image, and this shadow, or I should say this cyclonic storm is about 7,000 kilometers across. So that's more than half the size of the Earth. So this storm is more than half the size of the Earth, and its elevation, based on our estimate of this and looking at the shadow and the rest of the geometry, is that it's vertically towering up about 85 kilometers or more. And so you can imagine the kind of atmosphere you're dealing with if you were at Jupiter and you're flying a plane through it, or unlucky enough to be in a balloon, and you're looking at a thunderstorm or a tornado that is half the size of the Earth and 100 kilometers tall. So it is a truly towering beast of a storm, probably the biggest thing we've ever seen. And so this is what Jupiter is really faced with. Now, JunoCam, one of the things that's interesting is JunoCam is an outreach camera. We put it on in order to connect to the public, but it clearly has science value, and we're already reaping that. But it is primarily aimed at reaching out to the public and allowing the public to get engaged and process their own images and get involved in science, and also to do some artistic work with it. And we've already gotten that. You can go onto our website, You can see posted images that are raw. The public can process those, post them. Sometimes they're scientifically interesting, sometimes they just make an artistic gesture. And so I'd like to now turn to Candice Hansen, who's going to tell you about that public camera and how it's working to touch the public.
Thank you, Scott. So I'm going to be talking about JunoCam, which is the camera shown right here. And Scott's vision back in the days when we were actually just writing the proposal was to find a way to involve the public in the process of space exploration, the good days and the more challenging days, and to sort of live our lives with us. And so what we decided was that we would involve the public in every aspect of what an imaging team would ordinarily be doing. And so my first exhibit here is an image processed by one of our amateur community. So let me tell you a little bit more about how we're doing this. We have developed 4 ways for the public to engage with us in a participatory way, not a passive way. And so we have amateur astronomers uploading their telescopic images that they're taking here on planet Earth of Jupiter that we can then use for planning purposes. And the we in this case is the entire public, not just the tiny little imaging team. And then the discussion page is where we go to talk about the pros and cons and what's interesting of all these different atmospheric features. We will have voting coming in the future. It won't be November, it'll probably be February, maybe November. And then, but what I'm going to talk about today is the image processing piece of this. And you can see the URL right there, takes you right to this page. What we are doing with our little ops team is we are staging the raw data from JunoCam. So we get the data back in a series of strips, and we put the little strips back together again into red, green, and blue, and then we do a very preliminary color reconstruction that tends to have artifacts like the big slash you see in the picture above. Those are then anybody can download those images and they can do anything they want with them. And so what I'm going to share with you are some of the really fabulous products that are and then we tell them, please, if you don't mind, upload your contribution back onto the website for everyone to admire and learn from and use. You know, don't just stick it on your private Facebook page. We all want to share. And so here's a beautiful contribution where you can see that the processing that this person has done has brought out detail in the cloud features all the way from the terminator, the shadow, out to the bright limb. And that's actually pretty tricky to do. But in order to go a step further and help us really appreciate these features in the atmosphere, he helpfully put boxes around them and enlarged them. And so to really draw all of our eyes to these wonderful sort of pinwheel-shaped storms that Scott was just describing. There's a particular community at unmannedspaceflight.com that has been particularly engaged in all of this and incredibly helpful. And one of their members actually annotated his contribution with how he did it. So it's a community that's not only helping us, but talking to each other and sharing tips and what works best. I don't want you to try to read the fine print here. What I want to, the message I want to give with this particular choice is that we also have people jumping in to help us with the science analysis. And so these are all JunoCam pictures, but they've been labeled with features that have been followed from the ground over the years. And I'll just take a second here to point out this, here's that storm feature that Scott was just talking about. This particular, the way this particular image was processed by this particular amateur brings it out very nicely right here on the terminator. Here's another example where features in the JunoCam close-up images have been correlated, again, with features seen in the ground-based data, and that allows us to connect what we're seeing from our very different perspective to the historical record of the dynamics of Jupiter's atmosphere. Sometimes we get contributions where people have experimented with different color ratios, and this happens to be one of my particular favorites in the color choice selection that this person made. Here's a fun one. Does everybody see the happy face? The two eyes and the big smile? This is a reflection. Basically, this person mirrored the South Pole image to get the eyes and the smile. Do you recognize this one? Van Gogh's Starry Night? This is Juno's Starry Night. And this is one of the newest contributions. One of the things right now is that Jupiter is quite close to the sun. And so from the Earth, right now, we're not able to get images. So we've been taking sort of low-resolution images with JunoCam to fill in while the amateur astronomers cannot provide data from their own telescopes. And so here's a nice cylindrical map that we are going to post in our discussion page, and again, an amateur contribution. And
backwards.
Now it's time for questions.
So if you have any questions, please raise your hand, and when you get the microphone, please identify yourself before asking the question.
Thanks. Alex Witzy with Nature. For Scott, could you talk a little bit about what happens if you stay in a 50-day orbit for some time? What expendables are there on the spacecraft that would determine lifetime, and/or what does that say about radiation exposure if you are on this longer orbit? Is that more of a problem or not?
Sure. So as far as the expendable go, we don't know of any as far as that the extra time would prevent anything. We can stay in the 53-day orbit, and every subsystem can survive that. The extra time doesn't cause a problem. The radiation also doesn't change because the radiation that Juno gets is only around the closest approach, and so it's mostly orbit driven. So the number of orbits is what drives the radiation up, and the evolution of the orbits, which is also orbit driven and doesn't change a lot between the 14 and the 53-day orbit periods. So the radiation dose per orbit will be about the same. In fact, it might be a little less, in fact. And the duration, I don't think, causes an issue. So you can stay in the 53-day orbits and continue to collect essentially almost identical science that you would have gotten on the 14-day with respect to our main science objectives and goals. You do run into an issue over a long period of time if you just stay in there indefinitely, because eventually Jupiter will move around the sun, and the orbit plane will stay roughly in the same orientation. And so at some point, and this is a few years away, you will run into a place where you have a short eclipse of maybe 6 hours or something we've been able to see. So if you stayed in the 53-day orbit, eventually you would go into the shadow of Jupiter, and we would have to, if we were never going to change out of the 53-day orbit, we would have to go investigate how to get past an eclipse. We know we can tolerate some, but we haven't really looked at that particular length and duration.
Hi, Calla Cofield with Space.com. I just want to clarify something about with the bands. You said that they're similar, but there are also noticeable differences. But just to clarify, so far the team thinks that with those observations, you can definitely say that those bands are being caused by something below that first layer of atmosphere. I believe that's what you said.
I don't know if I said that they were caused by something below, although it is telling us something about the deep dynamics. I'm not sure I can say anything at this point about what causes those bands. It may be chemistry or composition, but whatever it is that's causing that is present at the deeper layers. And although it's evolving. So, whatever's tied to creating those bands is being twisted around by the dynamics to some extent, and allowing those bands to move or change and evolve a little bit as we go down to deeper layers. I don't think I can say anything about whether the bands are created in those layers or somewhere deeper down and then transported up. I mean, that's something we may be able to investigate in the future.
Yes.
Patrick So, Griffith Observatory. Are there any plans to take images of Jupiter's cloud tops at Perry-Jove?
Yeah, you want me to?
Sure.
Yeah. The answer is yes. We did actually take some pictures at Perry-Jove on the last flyby, but what we found was that we had not set our exposure settings to long enough. We're taking pictures of a cloud right near the shadow. So in a lot of ways, that was a test run for us, Perry-Jove 1, and so now we know, how much we have to boost our exposure time. So, I forgot to say something I want to add. We took a real leap of faith with this experiment with the public, that people would actually think this was cool and participate. And I'm really so pleased with the response that we've gotten. I really feel like our leap of faith was justified.
Yeah, let me add something so that you understand. So when we flew by for the first time with our science instruments on, which was August 27th, what we call PJ1, prior to that, we'd gone close to Jupiter, but everything was turned off because we were getting into orbit, right? We did an orbit insertion burn. So the first flyby on August 27th was not really part of the science mission. We had all the science instruments on, but what we wanted to do was test them, calibrate them, make sure we understand how they work close to Jupiter. And originally, this flyby that happens today was designed to actually change the orbit. And when we opted to go ahead and put on these science instruments, it was still sort of to just get extra science. Our overall plan didn't really start the primary mapping phase and data collection that goes into the gathering the science objectives until the fourth flyby, which wasn't scheduled for until another month or so. And so the data that we collected on PJ1, as Candy pointed out, was really a test case. We were using that time to test out exposure rates for the cameras, what are the right ones to use. We've never been this close to Jupiter, and all of the instruments had some aspect like that. Obviously, most of them got great science. You saw these incredible images that we got. I just showed you the microwave data. Each data set is remarkably, unique and discovery-like. We are seeing things that we didn't expect across the board. The magnetic field, the aurora, the gravity field, every one of them have produced outstanding new science results. But this all came somewhat serendipitously because this was really a calibration flyby. So we haven't even really started the main science. So there's a lot more to come.
Emily?
Emily Lochtwalla with the Planetary Society. Can you talk anything more about what the spacecraft reported that caused it to enter the safe mode? And then can you say anything about the results on, any science results on magnetic field or aurora that you've gotten from the first flyby?
So the data is still being looked at and trying to be understood, so I can't really even take a good educated guess as to what caused it yet. I mean, we've been able to make sure the spacecraft was safe. We've changed the data rates to a higher rate so that we can get the data down and analyze it. But I think it's too early to take a guess as to what caused it. It did happen pretty far away from Jupiter, and so, you know, my instinct is that it may not have been tied to the intense radiation belts that we're so fearful of. That doesn't mean that there isn't something else in Jupiter's environment that may have caused it. There's a lot there, even if you're far away. Now, as far as the science results, we're still analyzing. A lot of the stuff was brand new and discovery-like from August 27th. We saw some stuff on the Aurora. We released an infrared image that was pretty remarkable. I'll show that again at the talk later today. But we're still analyzing what all that means. As far as the magnetic field, it also, when we got really close, we saw that the magnetic field was stronger, and which means it's a little different than we expected. But we're still analyzing what that all means, and you may need more flybys to fully sort that out. So there are some great discoveries coming, but we're not quite ready to tell you what the interpretation is, because it's sort of work in progress. We are aiming toward talks at the AGU a few months from now, and the first science papers, and so we hope that we'll have more of this data interpreted and presented there.
Rick, do we have any questions online?
Yes, we have quite a few. I apologize if some of these overlap with some of the other ones. There's such a stream of text here that it's hard to sort it all out. This first set of questions comes from Dave Mosher from Business Insider. Well, actually, he just asked what do you think caused the safe mode, but that's been answered. So how long might the mission have to be extended if the mission, or if the engine is never fired and the spacecraft is stuck in 53-day orbits? Are you guaranteed some minimum number of passes, or are you guaranteed an extension or not?
Well, we know we can stay in that 53-day orbit as far as safety goes. We do run into the eclipses eventually, and those are, I think, in the middle of 2019. And so we can get, I don't think that happens until like 53-day orbits. So you get a lot of orbits, and you have a lot of time to study the rocket motor or decide if there's a way to get around the eclipses. And you can accomplish an incredible amount of science in 20 orbits.
A related question from Maddie Stone of Gizmodo is, how long do you have to decide, or how late can you decide when to switch to a 14-day orbit, or is there some point in the mission where you just kind of have to stay in the longer orbit?
There's no specific time that where you run out and you can't change to a 14-day orbit. That's one of the beauties of the flexibility we have in the design. We can do that at almost any time once we decide we're ready to do it. Again, you would need to do it sometime prior to the eclipse, or have some way to get through the eclipse if you did it really late. But that decision wouldn't happen until, I mean, you won't get to that point where you have to make that kind of a decision until 2019.
Okay, and here's a quick question from Alex Teleshev of RIA Novosti in Russia. This question also for Scott. What do you think at this point is the worst case scenario?
The worst case scenario is I have to be patient and get the science slowly. Where science is still going to be obtained in the exact same way that we had planned. The 53-day geometry is pretty much the same. The science opportunities are all there. There's a plus side. We have more time to analyze and interpret the science. And so you can dive in deeper to each data set than you were going to be able to. But the bottom line is I have to wait, and I'm generally impatient, and most of my science team are.
Okay. Any other questions from here? There.
Matt Kaplan, also from the Planetary Society. For Candice or Scott, with that remarkable image of the cyclone on the Terminator, or for any other reason, are there new science objectives for JunoCam that would complement the intended public use?
So we've always thought that we would do some science with JunoCam, but because it's one of the main goals is to do the outreach, what I have told my colleagues is that if they want a picture of a particular storm or belt or zone, they need to put a point of interest into our database. They need to discuss why it's important, and then they have to round up the votes when it comes time to vote and be a part of the process. And I think that will add a lot of richness to the conversation, because we'll have scientists advocating for their targets in the midst of a public discussion. And I think we're all going to have fun doing that.
Okay, one last question. Emily?
So Emily Lochtawala again. Candy, I know that your plans have now had to change for imaging for going through the next apogee and next perigee. Can you talk a little bit about how your imaging plans have changed? When's the camera going to turn back on? And when can we start seeing rapid release of the raw images?
Yeah, I mean, we thought we would have some today. There is a piece of spacecraft data that we have to wait for to complete the initial processing. That has to do with the rotation rate of the spacecraft. So that is like 2 days. So our plan on every perigee is that as soon as we get that spacecraft data, we start posting our images. So there's no holding back or validating or anything like that. They'll go right out as soon as we have that last piece. Now, obviously, we won't have any going out. It would have been Friday of this week. At the next perigee, however, we will plan to take images. One of the things that we learned from the first perigee flyby is that it's very important to get context. So we will take a series of images as we're approaching the last 10 hours, and then we will do a series through the perigee pass, and then for a few hours afterwards. Now, we've been debating about putting that out for a vote because we're not really quite done with our testing because of some of the things that we learned at perigee 1. We want to try some new things the next time we image. But we probably will put maybe half the data volume we'll allocate to be chosen by vote and reserve half for testing. But that's not our plan going forward. Our plan, as soon as we've figured out how to really get the best out of the camera settings, then we will have it all by public debate and voting.
Okay, with that, we'll conclude this press conference. We thank David Schurr, Scott Bolton, and Candy Hansen for the wonderful presentations, and everyone else for being here. Please join us tomorrow at 12:30 for the last press conference of this meeting. We have a wide variety of interesting topics tomorrow. Thank you.